I'll show you what I mean by that. Within the eProcess block, there's a 1 byte field that says whether this thread is alertable or not. This is taken from the MSDN. This is Microsoft's explanation of the different types of APCs. There's kernel mode APC, user mode APC. And when they will and will not, when APCs will and will not be delivered to a particular thread. I won't go into all the idiosyncrasies of this. So here's the code to find an alertable thread so that we can schedule our APC. You pass in the eProcess block, or a pointer to the eProcess block of the target process you want to inject within. Then you find the list of threads within that eProcess block by dereferencing from the thread offset. Once we're at that point, we have a pointer to a eThread object, and we can simply walk it through the do loop there, do while. We can walk it looking at its alert offset to see if it's equal to 1. If this is true, then we return the address of that eThread because we need that when we're scheduling our APC. I'll forgo the demo till the end because I want to tell you about the what's going on in the demo when you see it spit out a bunch of information. So here's some of the motivation for our memory analysis. It has to do several different things for us. We know that APIs can lie. We also know that you can, for example of how you would do this is in the PEB, there's the loaded module list. You could simply remove yourself from that, and your DLL will disappear from Process Explorer and all these other tool sets. You can also hook the virtual memory manager so that if someone tried to do read process memory or something like that, which actually Mark Rusanovich's Process Explorer does, you could subvert his reads so that the tool reads somewhere else. Also, APIs aren't available in classic forensics. What I mean by classic forensics is usually offline or dead forensics. So we need to, this is what motivated the development of the analysis tool, and this is what it had to do. So it couldn't rely upon any APIs. One side effect of this is that we should be able to look at both live memory and a dump of memory exactly the same. We don't have to rewrite any of our code because if we're not using APIs, that means we have to do all the memory translation ourselves. We also don't rely upon any PDB symbols from Microsoft about where certain structures lie. Normally, what will happen is tools will use linked lists and so forth to find all processes or to find all drivers. These linked lists are exported, but only if you have the PDB symbols to find the address of the export. So we don't use that because OS has changed quite frequently. We want to try to derive as much as we can from just raw bytes. So what do we require to run? Well, we have to have access to physical memory, or some other tools had to give us a dump. There's already tools that will give you a memory dump. DD will do it for you. We also will acquire memory, just like DD does as well in our tool. We need to be able to derive the version of the OS, because the version of the OS determines how things are set up in memory. We need to be able to find all processes and threads, and to enumerate things like handles, DLLs, ports, etc. If we can enumerate handles, which we won't show you in this demo, but our tool does it, the enumeration of handles will tell you, hey, this process has a handle to that mutant that Chris showed in the example of the rat tool. So DLLs is what we're going to concentrate on here, and we'll talk about how we found those in a moment. So first of all, to do virtual to physical memory translation, you have to determine if the system is PAE or non-PAE. That changes the way you interpret the page directory tables and the page table entries. We need to be able to find the page directory table base. This is process specific. Every single process has its own view of physical memory. That's how the OS protects processes from one another, because they don't have a shared address space. And we need to translate prototype PEs, and eventually when we begin to dump the memory, like once we find an injected DLL, we might want to grab that area of memory, write it to a file, so that we can throw it into a reverse engineering tool set, such as IDAPRO and whatnot, in order to figure out what this malware does. So we're going to need to be able to see if the region's paged in. If it's not paged in, we need to be able to go to the paging file and pull out the bytes that we need. Now, to do this, you would, if you're on a live system, we have software where we read the raw disk to get access to the paging file. If you were on a dead system, you would obviously have to have acquired the disk image as well as the memory image. So what do we do to find the system process? Or what does the system process give us? If we can find the individual system process that exists on this host, we can derive most of the things that other tools have to hard code. So for instance, the system has its own, it has one single version of the page table base for the OS itself. So we can find that. We can find the link, or the process head, which is the PS active process head, which would point to all the processes on the system. It's a linked list. We could also find the handle table list head, which in the past others have used to find rootkits by traversing the handle table list, and so on and so forth. So here's our algorithm for finding the operating system version. First of all, we need to find system. To find system, we simply look for a string, because system always has the same name. From that, we walk backwards, and we can find the beginning of the process environment block. If we find the spatial difference between the address of the string name and the beginning of the eProcess block is actually enough to tell us the major version of the OS. So that will tell us whether we're running on Windows XP versus Windows 2003 versus Vista and so forth. Oops. Sorry about that. Yeah, scroll real quick. So, are there any questions up to this point? Or gets back? Okay, so let's move on. One drawback of doing it, the analysis this way, is that you'll find ghosts. And this hit me early on in the development when I was analyzing memory, and others have talked about this. At the BlackHat Fed talk, there was a talk by Aaron Waters and Nick Petroni, in which they talked about finding, more or less, you could subvert memory forensics by just throwing a lot of garbage into memory that looks like things. So I was finding ghosts, and the reason I was finding ghosts is because I had 3 copies of WinDbg open doing crash dump analysis, as well as 2 VMs running a separate OS. So I kind of, from the perspective of the analysis tools, I had 6 different OSs running in memory. So you have to be able to eliminate the ghosts. And one possible solution is that kernel addresses are global. So from the system process, you can find its process table directory base, and you can also find, from that you can translate, excuse me, you can translate addresses such as PS active process head or PS initial system process and so forth. Since these are kernel addresses, They should exist in memory, and the translation should succeed. Now, before I can try to test that theory, I have to figure out whether the system's PAE or non-PAE, because I have to do all the address translation myself. So normally the way this is done is that the CR4 register on the CPU in bit 6 determines whether PAE is enabled or not. However, since we're running, either we're analyzing a dump of memory or we're running on a live system, but remember the requirement was we really use no APIs. We don't run any code that deals with the analysis itself on the live system. Therefore, we don't have access to the CR4 register. So what's the solution to this? Well, you can look through memory for a long time, and believe me, I did. And you can find that there is a processor control region. The processor control region is in the kernel address space. It points to a K processor, a KPCRB. KPRCB contains a K processor state. K processor state contains K special registers. And K special registers contains the saved CR4 value. This works beautifully every time on a crash dump. So if the machine blue screened and we got the dump, works perfect. Never works on a real system. A live system that's running, that CR4 isn't updated, or I couldn't determine that it was updated in a reliable manner. The OS just wasn't updating that field, so I was screwed. It was all zeros. So how do I determine CR4? Well, it turns out that within that processor control block, there is a CR3 value that is saved. So that means that there exists some random process on the host, on the live system, whose CR3 value, which is the pointer or the address of the page directory table base, it is saved off. It's right there if I follow the processor control block. Now, what does that get me? That's the page directory table base. So if you go to the page directory table base, you can create a heuristic for determining whether CR4 is enabled or not. Because if PAE is enabled, the fields are a bit wider and so forth, and you can notice differences that are detectable in a nice way. So now I know the major version of the OS. I know whether I know whether PAE is enabled or not, and I know I've been able to eliminate the ghosts. Because when I found the page directory table base, and I did the translation of things like PS active process head, then if it failed to resolve to a legit address that was present in physical memory, then I know that I'm working with a ghost, so I can eliminate it. Now let's talk about finding injected DLLs. Again, we aren't the first to do this, but we are fairly close to doing it simultaneously with others in the field. There will be some tools released by Aaron that will demonstrate walking VADs, and we'll talk about what that is, and we do it as well.